Okay, so now we're going to start again. Okay, so this is the second lecture of Math 1203. So last time we didn't really do anything. I sort of just introduced you to stuff and gave you a quiz. And as I said, try the blank version on the website and then check your answers. For now, we're actually going to start something. We're going to do section 1.1, functions and their representations. So between tonight, late probably, or tomorrow morning, I'll post a video for this. I want you guys to actually watch it. Let me know if the view is okay. You can read everything on the board, and I might need to change how things are set up. But yeah, functions and their representations. So let's talk about your definitions. What is a function? Do you remember what a function is? Anyone know what a function is? How to describe it? What does it mean to be a function?
Well, you put something into a function and you get an output.
You put something into a function, you get an output. Is that all? What makes it a function? Yeah?
So like if every input can only have one output.
Okay, that's a very important part. So you are correct, but it's not the full picture. Every input can have only one output. Okay, so I put in a number in, I can only get one number out. If I get several numbers out, it's not a function. What else can you tell me about functions? But I think those two ideas kind of encapsulate the definition, but there's some other stuff that we'll need to talk about. Okay, so a function is a rule that assigns to each, as in every, element in one set. We call that set a domain. Exactly one element in another set. That set we call the codomain. The set of elements in the codomain that are assigned are said to be in the range of the function. So that's what a function is. It's a rule that connects things in one group to things in another group, such that every element in one group is connected to only one element in another group. And this is sort of a mathematical definition, but functions are important in general. Functions really describe relationships between objects, but it's a very special kind of relationship. It's a relationship in which every object in one group is only connected to one object in the other group. And whenever you have something like that, you can call it a function. And it can go far beyond mathematics. In fact, mathematics is really just kind of a model for other situations. But you can really think of a function as describing a relationship between two groups in this particular way. And it can apply to anything. So I can do something like being a father of, right? The quality of being a father is not a function. Why? Because if I connect fathers to children, there's not only one child. It's possible for me to have more than one children, okay? However, being the child of would be a function, right? If you're talking about your biological father, you only have one, right? So it's a function going one way but not the other way. You can apply functions to anything. You're just talking about certain kinds of relationships that have a certain specific kind of property, okay? So to kind of imagine that, you can talk about, here's a group that we call the domain, and here's another group that we call the codomain. And a function is just a rule that takes guys over here and to each of them, they connect them to one guy over here. They might connect it to the same guy. The important part is that there's only one line from everyone here going to over there. Right? The set of guys in here that we get assignments, they are called the range of the function. So we call that the range of the function. Anything that's might be in this group, but they don't get connected to anyone, they're not in the range of the function. They're just in the codomain, but not in the range. So that's like a pictorial representation of a function. It's a representation of a relationship between objects in two groups, such that each member in one group only has one connection to another member of the other group. We call that a function. Okay, so it's a special kind of relationship. Right? There are many other kinds of relationships. You don't have to have functions. Okay, so something like, so if you have something like this, connecting to that, connecting to that, connecting to that. That's an example of a function. You can have this connecting to that. Everyone connecting to one point, that's still a function. Something that's not a function would be something like this. So once you figure out that how the objects are connected, you can realize whether it's a function or not. Something that's not a function. And it's possible for someone not to get chosen, that's okay too. But something that's not a function would be something that looks like this. That's an example of something that's not a function. That's another example of something that's not a function. Why is this not a function? Yeah?
Because one thing in the domain is connecting to two things in the codomain.
Which one are you talking about?
The one that's not
This
a
one?
function. Yeah, that's why it's not a function.
Yeah, because here I have this one thing getting two assignments. There are two possible values for it. That means it's not a function. What makes this not a function? Yeah?
The last one isn't connected to anything. There's nothing for it to connect.
There's nothing for this to connect to. So the important thing in one function is that everybody in the first group must get an assignment. Not everyone in the second group has to get one, but everyone in the first group has to get one. The fact that this guy is not connected to anything makes it not a function. Okay? So it's a very special kind of relationship. So you're taking everyone in one group and you're connecting each individual in that group to somebody else in another group, such that each person in this group only has one connection, but they have to have some connection. Okay? So that's a function. That's what we call a function. So any relationship that has that quality, we call it a function. And the idea being that you should be able to apply this in non-mathematical situations as well. Okay? But that's kind of how you want to think of it. So some more definitions before we move on. The elements in the domain are called inputs. We often use X to represent, often as in not always. I can have other letters, right? But usually we think of them as X and Y. A lot of times we get married to this fact that, oh, Y equals f of X, but it doesn't have to be X. To represent an arbitrary domain element. In this case, X is called the independent variable. So That's a phrase you might hear me say every now and then. I don't want you to be confused whenever I say, oh, the independent variable, I'm just talking about a representation for the guys in this group. Right? An independent variable can take on all the values in this group. So the domain is the set of possible inputs that you can have, and they are represented by, for example, the variable x. The elements in the range are often represented by y, right? In which we call this the dependent variable, because it depends on what value you plug in for x. The range is the set of corresponding outputs. So we're kind of getting more mathy now. So in general, I want you to think of a function as just some relationship between groups of elements. It's a special kind of relationship between these two groups, in which every element in one group is assigned exactly one element in another group. But now we're going to move on, slowly creep into mathematical notations. We can name functions. We usually name them by a letter. So for example, if I write y equals f of x, right, that's read f of x, it's not a multiplication, it's a notation. This means a function of x. That means y is the output, or dependent variable. Dependent variable. F is the name of the function. And x is the independent variable. That is the input. So when I say y equals f of x, I'm saying there's a function that I call f that takes input values x and outputs values called y. And so how you can think of a function is just this machine that applies a rule to things that you put into it, and exactly one thing comes out when you put one thing in. So a function is just this thing, right, I can call f of x, where x comes in and the y comes out. And only one thing can come out for each individual that you put in. Okay. Let's talk about representing functions. There are several ways to actually write this idea down. Okay? So several ways we can represent when a relationship like this is happening. One way is what we call a mapping diagram. And it's what I was using earlier. So this is where you literally draw a picture of two things and connections between them. So for example, if I say f of x equals x plus 1, right? That's my rule. I can actually draw that as, say, 1, 2, 3. So this is the domain. That's the codomain. Okay. So this is the function that says take input, add 1. Right? That's the rule, right? You give me something, what I'm going to do is I'm going to add 1 to it and tell you the output. So 1 would be connected to what?
2.
2. 2 would be connected to 3, 3 would be connected to 4, and so on. Okay? And that's a rule. And I can represent that rule by actually drawing this picture, writing out a few examples. That's one way to represent a function. It's not going to be very common for us to do that in this class, but it's possible. Another way is to use a table to represent functions. So I can, if I have that function f of x equals x plus 1, I can actually write that as a table. I can tell you what all the x values are and their corresponding y values. So 1, 2, 3, the y value output will be 2, 3, 4, etc. I might have a table of values, and that can represent a function. And as long as you don't have a repeat. If you have another row with 2 in here, it's not a function, right? You can only list things in this column one time, but everyone has to be listed. Another way you can represent a function set of ordered pairs. Ordered pairs is a fancy name for coordinates. So if I have f of x equals x plus 1, I can write that to say f is, and I can write a set. If I have 1, it connects to 2. If I have 2, it connects to 3, and so on. Right? And I can write a set of points, right? Where the first coordinate is the input value. The second coordinate is the corresponding output. So we can have a list of coordinates, and that's another way to represent a function. You can have a verbal way to represent a function. Basically, in words, what the function does. Add 1. Right? This is the rule. Five. Graphs can represent functions. So for example, if I have the function f of x equals x plus 1, the independent variable always goes on the horizontal axis. The dependent variable goes on the vertical axis. So 1 would go to 2, and you can plot that point, right? 2 goes to 3, you can plot that point. 3 goes to 4, you can plot that point, right? And if you want to get everyone in between, if we're looking at the real numbers, then we can connect all those lines. So that graph can represent a function. And how you know if a graph is representing a function is it passes what we call the vertical line test, which means no matter where I draw a vertical line, it will touch the function, the graph, at most one time. Right? So that's how I know that something is a function. So for example, a circle is not a function. Right? Because I can have an x value here that I cross a vertical line, well, whatever. So let's say this is x squared plus y squared equals 4. Right? So a vertical line will cut this in 2 parts, which means the number 1 would actually connect to 2 things. Right? It will connect to radical 3. It will also connect to minus radical 3. So in this group, the number 1 maps to 2 things. Radical 3 and minus radical 3. Which makes it not a function. So a circle is not a function. So not all graphs are representations of functions, but ones that pass the vertical line test. So graphs, very common way to represent functions. So most of the time I'm going to actually either be drawing a picture for you, or the next common way to write a function is with a formula, which I kind of used already. Or you might hear the term algebraic. So this is just to say f of x x plus 1. This is a function that says the rule is to add 1. Okay. This is also common. 5 and 6 will be commonly used. In fact, usually to solve problems, we're going to want to use either one of these two. So if we're given something in some other way, we'd probably want to be able to draw a graph from it or come up with a formula for it, and that will allow us to solve problems. Okay. Did I say anything strange to anyone so far? We've all kind of seen this before, right? Functions. Let's actually take a break from all these definitions and let's do a problem. So these will be common representations and they are often the most useful. So we're going to use a problem here. We're going to do a problem here. It's going to be a word problem. We're going to solve it with the use of functions. Some of the parts we're going to throw ourselves in the deep end and really kind of try to see if we can figure things out. But later on, we'll go over this stuff. Okay, so here's an example of a situation where we're going to use functions. So the first two parts, I just want to know that you're interpreting things correctly, and then part C, we're actually going to solve a problem that's going on, and we're going to use functions in order to get it done. It's a word problem, so there's going to be a little bit of writing here. We've been doing writing the whole time. Okay, so this problem is about Jhevon's hot dog stand. Okay, so let's pretend I own a hot dog stand. I sell hot dogs on the weekend. Okay? I also noticed some things from selling these hot dogs. I've noticed that he notices if he charges $3 per hot dog, he sells on average, what were the numbers I put? 50 in a day. Alright, so I charge $3 per hot dog. I can sell reliably around 50 hot dogs. If he charges $2 per hot dog, he sells 80 in a day. By the way, this is just some statistics being thrown at you here. So that's where statistics would come in. That's where this data would come from, right? I actually measure things, right? And I sell $3 per hot dog for a while, and I notice that I can sell around 50. Then I sell for $2 for a while, and I realize, I can sell about around 80. Okay, so that's the situation. Okay, so now A. Define a function which I'm going to call h of p. So again, I don't have to use x and y and f. I can call it whatever. To represent the number of hot dogs sold per day at price P. Okay, now here's the question. Interpret. When I say interpret, I mean explain to me in words. When I say h of 3, what am I saying? So I said h of p is a function that represents the number of hot dogs I sell at price P. How can we interpret h of 3? How can you say in words what that would mean? Yeah?
You're selling hot dogs at $3.
Okay, but what would this be?
Oh, it's the function, right?
Yeah, but what does it represent? H of 3. Yeah?
50?
Almost. That what you're doing is evaluating the function. I just want you to interpret it. Don't give me the number, but in words. Yeah?
The total hot dogs sold per day when you're selling.
Total number of hot dogs sold per day. When the price is P. Well, when the price is 3. So the answer to that would be 50, but to give a specific answer, you're saying you're evaluating the function, which is not what I'm doing. I just want you to interpret. What would, if I write this down, what am I talking about? We'll get to actually finding specific answers pretty soon. So I have this situation and I'm modeling it with a function that tells me the number of hot dogs I sell at a certain price P. If these are the only two prices I'm willing to sell for, what is the domain and range of H? So tell me, what is the domain of H in this example? What is the domain? Yeah?
2 and 3.
2 and 3. Remember, the domain is a set of possible inputs. I have defined a function h of p. Remember, in this notation, the guy on the inside is your input. The input is p, which I tell you is the price. The possible prices are 2 and 3. Therefore, those are the guys in the domain. 2 and 3 are the domain elements. What about the range of h? What are the possible outputs for the inputs 2 and 3? Yeah?
50 and 80.
50 and 80. That's it. So here's the actual problem. So this is the problem we're going to be tackling. What is the best price? Okay. So I have data for when I sell it for $2. I also have data for when I sell it for $3. But are those the best prices to sell it for? How much should I be selling it? Ideas. How would we tackle this problem? What is the best price to sell a hot dog for? How would you interpret best price first of all? Yeah.
I'm not sure, but I would say like to try to find like the revenue, like how much you're making.
Revenue, the most money, right? Like,
Yeah.
I'm doing a side hustle, I need money, okay? So the best, in my opinion, would be whatever makes me the most money, okay? So best, I want to know, how can I make the most money, okay? How do we do that? How do we do that?
You multiply
Multiply what?
your, like, since for the 2 hot dogs you get 50, you multiply 2 times 50 and you'll get 100. And that's how much you're making.
When I sell it for $2, how much did I get?
It needs to be two.
Oh, sorry, 80. That's what I meant. Sorry,
Okay.
I got confused.
So if I sell it for $2, I'd make what? 160. If I sell it for $3, I'd make 150. Is 2 the best price? Read the problem, right? I'm willing to vary my price. So I'm not married to only selling for 2 or 3. I'm willing to sell it for $2.10, $2.50, $3.10. How would I know what I expect? How do we tackle this? So I'm willing to change the price from either 2 or 3, right? I know for $2 I'm going to make 160. For $3 I will only make 150 per day, but I'm willing to change, and I also have this expectation. Given those two, how do you think we try to find it? Yeah?
I made a graph.
Okay, make a graph. How do we make a graph?
Using these 2 points,
What would go on the horizontal?
2 and 3.
Right, so P, which is the input, I know because it's H of P, and so my H would go here. I know for 2 and 3, 2 gives me, what, 80. So that would give me this point here. 3 would give me 50. That would give me this point here. Now what?
Draw a line,
Draw a line. How do you know to draw a line?
because you said it's linear.
Because I said there's a linear relationship. Linear means the graph is a line. Okay, we have that function. What do we do with it?
Do you know what the y-intercept is, so you know how many you're starting off with, if you saw none?
How would I find the y-intercept?
At what point the line crosses the y-intercept?
Yeah, that's what it is, but how do I know, how do I find it? Yeah?
When x equals 0.
Well, when P equals 0, sure, but okay, P equals 0 is what? Like if I'm selling free hot dogs, like how do I know how much I can give away? How would I figure that out?
You write a function and then put p at 0 and then plug 0 in.
Okay, we need to know the function. How do we find the function? Yes?
Slow.
Okay, so it's a straight line, which means it has the equation of a straight line, y equals mx plus b. So we need to find the slope, which is the m, and then blah, blah, blah. Okay, so how do we find the slope?
Oh. y2 minus 1.
Yeah, y2 minus y1 over x2 minus x1. Technically here it's h2 minus h1 over p2 minus p1 or whatever. Okay, we get the idea. The rise over the run. Okay? So what is the rise here? The what? The second y value is 80 minus 50. And that corresponds to 2 minus 3. Right? What is that? 80 minus 50 is 30 divided by -1, so it's negative 30. Now what? Yeah?
You can plug it into y equals mx plus b and solve for b.
Okay. So So there are two ways to approach here. I'll show you both of them. You can use hope the camera's catching this. One way is to use y equals mx plus b, which is fine. And then you kind of plug them in, right? So we know that, and we know that m in this case is minus 30. So I can plug in an output. So we pick a random point. So I can pick the output for 80 equals minus 30 times the input, which is going to be 2 plus b. And so this would mean that my b is going to be 80 plus 60, right, which is 140. So I know that my h is equal to minus 30p plus 140. That's one way to get to the formula. Another way, which in some contexts, in most contexts actually, I would think this way is nicer. There's another formula which is equivalent to this one, y minus y1 equals m x minus x1. And then you plug in all the numbers all at once, right? So you have y minus y1, plug in 80, minus 30, x minus x1, which is 2. And you'd have y minus 80 equals minus 30x plus 60. Then you add 80 to both sides, you get y equals minus 30x plus 140. You get the answer right away, which is the same as that. Either method is preferable, but this method is okay. There are a lot of times where I won't require you to actually solve for the y, and this would be okay as an answer, so it will save you some work. And so there are many contexts in which I like this. Okay, but either way, that is going to be the equation of that line. Okay, so now what?
You start plugging in like your x's.
What x's?
If you're trying to find like the best price, I would say to like go down or to go up.
Okay, and what would happen?
Then you'd get more values on your y's, then you can then determine the best price.
You could do that. Is that the best approach? You could do that. It'll take you a lot of work though. Give me another approach. What are we trying to do? Let's start there. What are we trying to do? I think you mentioned it earlier actually.
Find the best price.
Yeah, but what did best? Remember we interpreted best in terms of?
Revenue.
Revenue. So we want to get the most revenue is the idea. How do we find the revenue? How do you find how much money you make by selling the hot dogs? What's your idea? Yeah?
Would it be H times P?
H times P, HP. Right? So we have one rule that gives us the H for a certain T, but in order to answer this question, we have to develop a whole other function. We developed another rule to get how much, right? Basically, the number of hot dogs times the price per hot dog. That's how much money I'm making. Right? This is what we call the revenue. We'll talk about this later on, but I just want to see how much you guys can reason through this. Okay, and what do we know? What do we know about H? I actually know what it is. Minus 30p plus 140 times p. So this is a formula that tells me how much money I'm making. What do I do with it? What kind of formula is that? It's also a function. What kind of function? How do you know it's a quadratic? How do you know it's a quadratic?
Because if you like multiplied it, when you get like 30p squared.
Okay, so now we can see it's a quadratic. It's a linear, it's a polynomial where the highest degree, the power is 2. So we know that's a quadratic. Okay. Now what? what does this look like? What would it look like? Yeah?
It'd be upside down.
It'd be an upside down parabola, right?
This is the highest.
How do you know it's going to be an upside down parabola?
Negative.
The coefficient of the square term is a negative sign, so it's upside down. If it were positive, it would go this way. So now do you know what we're after? This point right here, the vertex. How do we find the vertex? So at the end of the day, we want vertex. How do we find the vertex? Huh? Complete the square. We could. There's a shortcut. There's a formula for the vertex. Anyone remember a formula for the vertex? Yeah.
Negative b over 2a.
Minus b over 2a. The vertex, the input for the vertex is minus b over 2a. Right? Where a is the coefficient of the square term, b is the coefficient of the linear term, and c would be the constant. In this case, c is 0, but we don't care anyway. So if I take minus b, minus 140, divided by 2 times minus 30, that will give us the p-value that we need. So the 10s would cancel. This is minus 14. It'll end up being 14 over 6. Can we simplify that? What's 14 over 6?
7 over 3.
Sure, it's 7 over 3. Give me in terms of money notation. Yeah?
Roughly $2.33.
$2.33. Under these assumptions, the best price to sell my hot dogs for is $2.33. Now, consider the fact that we actually use functions to solve this problem, which you might not have thought of before. Let's say I come to you as a friend, man, I'm selling hot dogs on the weekend, I notice I'm $2, this is what happens, $3, this is what happens, what should I sell it for? Now, you could tell me to do a couple things. You could tell me to, just keep trading in the price. $2.01, $2.02, $2.03. Do all of those for a few weeks and then see how much you're selling, right? Or you could just immediately tell me, I got it, $2.33, right? Just like, wow, how did you do that? Functions is how we did it. Being able to draw a graph to describe the situation, coming up with rules to determine what we want, what we're after, and then actually using the mathematics, and we can get an answer. We can know what the answer. It didn't take trial and error. We actually calculated it. Okay? Now, there were some assumptions. First of all, I assumed there were a linear relationship, which there's not always linear relationships. Okay? But this is a very simplified problem. I just wanted to show you how a function can just come into a word problem. You have this problem, like how much should I sell my hot dogs for? It turns out you can actually use functions to figure that out. Okay? Because there's a relationship between the number of hot dogs sold and the price P, that is a function relationship. And you can use that to your advantage. We use drawing pictures to our advantage, as well as finding formulas to our advantage, recognizing the kinds of formulas. Right? So once I know it was linear, oh, that's the kind of function, it must look like y equals mx plus b. Then you get to the revenue, which is what you're after, you realize, oh, that's a quadratic function. I know about those too. Okay. Here's another question that you may or may not know the answer. Maybe some of you have done calculus before, might know it. If I were to use calculus in this problem, where would I have used it? Yeah?
I took the derivative of the revenue equation in the middle.
Mm-hmm. And what would the point of that be?
Well, once you take that, then you set R to 0, and then you solve for P, because there would only be one P.
Mm-hmm.
So it would be pretty
And the
easy to
P you
solve.
would get is what?
It would be the same, 7 over 3.
Right. So in other words, if I wanted to use calculus here, it wasn't necessary, it would have happened here. Getting to that number is where calculus would come into play. Okay? Now think of all the things we did to solve this problem. Calculus would have just happened here. Everything around it was algebra. You have to remember how to graph things. You have to remember to recognize quadratics. You have to remember the equations of lines. All right, this is what I was saying in the first lecture. People fail calculus because of algebra. The majority of what you're doing is algebra. Your calculus will only help you with one little part. Right? Calculus would provide a way to find the highest point or the lowest point in general, because not all kinds of functions has a nice little form like this, right? This was a quadratic, and we happen to know a nice formula for quadratics to get that point. But if this function were something more complicated, and we don't have a general formula, calculus is what we would use to get this. Okay, so it's very important that you guys go over that quiz and really get your algebra under control, because the majority of what you're doing will be algebra. Calculus is a relatively small part of the problem solving process. Okay? There are some things that it's good for, where it's useful, and we will describe those things when we get to them. But, yeah. So that's an example of how we could use functions to solve a word problem. Any questions? Okay, let's move on. Now I want you all to, at the end of the day, go over this example and make sure you see play by play why I did what I did. Make sure you understand, and if you don't, you can ask me questions or try to figure it out. Let's move on. We're going to describe some other things. We're done at 1:15, right? Let's talk about evaluating functions. Basically, this is the process of figuring out the corresponding output for a given input. Right? So that was like what someone was saying earlier when I said, what is h of 3? If you gave me the answer 50, what you did was you evaluated the function. That means I asked you, when 3 is the input, what is the particular output? You tell me the answer 50. What you did was evaluated the function. So basically, if you have a formula, you do this by plugging in the input and computing the output. Okay, so that's called evaluating a function when you do it. So let's do some examples. So here I'm describing a function to you, f of x. It is x squared plus x plus 1. I want you to evaluate so when I ask you to evaluate, it's different from me asking you to interpret. That's what I want you to do. Usually when I say interpret, I mean explaining in words the concept of what this function is after. But evaluating is a different story. You want to find the specific answer. Evaluate f of 1. What about f of 3? What about f of a? Okay, how would we evaluate this function f of 1?
Just plug 1 in for x.
You plug 1 in for x, right? So if x is here, it's you square it, you add it, then you add 1, right? So 1 is just going to replace the x's everywhere. Right? Each instance of x is replaced by whatever is in the parentheses over here. This is going to be 3. Notice that here I used parentheses. We spoke a little bit about parentheses and their importance in the last lecture. Right? Use parentheses. Strictly speaking, I didn't have to here, but let's be on the safe side. Right? There are cases where not having parentheses might be giving trouble. What about f of 3?
13.
Jeez, don't skip on me. What do I do?
Plug in the 3.
Put the 3 for the x. 3, 1. So that would be 9 plus 3 is 12 plus 1, that's 13, lucky number. What is f of a? Again, just replace the a for x, so it's a squared plus a plus 1. Okay. What about f of x plus h? What's f of x plus h?
X plus h squared plus x plus h plus 1. No, parentheses wrong.
Right? Everywhere I saw that x, I replaced it with an x plus h. Common mistake here is for students to just copy down the exact same thing and then add an h at the end. That is not f of x plus h. This is f of x plus h. Right? There's a difference if the parentheses is here versus here. Right, so just adding an h to the end is not how you calculate f of x plus h. F of x plus h, how functions work is whatever I put in the parentheses here, it replaces every instance of the independent variable in that formula that we have. Okay? Let's simplify this a little bit. How would I simplify that? What is this guy? X squared plus h squared, right?
No.
Yeah, Seeing was going to say yes, I would throw the chalk at you. Okay. What is x plus h squared? X squared plus 2xh plus h squared. Right? So you can do the FOIL, you can FOIL it out, but it's nice to just know that formula. A plus b all squared is a squared plus 2ab plus b squared. Okay. This guy, I can just remove the parentheses, there's a 1 in front, so that's just plus x plus h, and then plus 1. Okay. That would be that guy. What about f of a squared?
Would it?
Hmm?
We plug in ace.
A squared squared.
Plus a squared plus 1.
What's a squared squared?
A to the 4th.
A to the 4th. I multiplied these two. It happens to be the same as 2 raised to the 2, but that's not how you do it, right? We'll talk about laws of exponents again later, but when you have something to a power raised to another power, you multiply the powers, right? So that's 2 times 2. What is f of minus a squared?
Would it be negative a4? Well,
Huh?
Positive.
Positive or how do you know? Again, you just follow the rule, right? Think of the x's as placeholders for things you want to put in. So if I put in a minus a squared and a minus a squared, now I have the idea where I'm squaring a negative. What happens? It just becomes positive. And so this would be just a squared. This one, though, is minus a plus 1.
You put negative a squared.
Negative a squared. And this is the So this is like on the quiz when I asked, I don't remember which numbers I asked specifically, but I asked something like minus 3 squared versus minus 3 squared. Right? They're different, right? This one is minus 9, while this one is actually positive 9. Right? It's important for you to know that the difference. Okay? So just because a minus is here doesn't mean the minus come out here. Follow the rule and you have to replace this entire thing with the x. And because you remember to put it in parentheses, you end up in this situation as opposed to that situation. So it's important for you to be careful when you're doing this. Okay. So that's why I said just open parentheses and put the thing in. Open parentheses and put the thing in so you don't end up making some sort of silly mistake like this, which in the grand scheme of things can cause a lot more trouble. In particular, it can cause a lot of trouble with what we're going to discuss next. We're going to talk about what's called the difference quotient. For a function f of x, its difference quotient is the function. There are two main ways to write this function: f of x plus h minus f of x all over h, or f of b minus f of a over b minus a. Now I assumed you guys have seen things like this before. Some that they would have asked you in algebra class to calculate, and maybe also in pre-calc class, and they never told you why. We'll see why this expression is important in this class. All right, we'll talk about where it came from and why it's important. So f of x plus h minus f of x over h. This is used more commonly. When simplifying, things you want to know, when simplifying this expression, you need to make sure that whatever simplifying you do, you need to cancel the h. So it's not considered, if I give you, hey, find the difference quotient and simplify it, it is not considered simplified unless you cancel that h in the denominator. And when we talk about where this function comes from, you'll realize why you want to cancel the h in the denominator. Okay. Spoiler alert, at some point we're going to want to plug in h equals 0, and you can't divide by 0. Okay. This guy here used when computing what we call the average rate of change. For what reason, I don't know, it's traditional. Right. So for some reason, when they're computing the difference quotient in this context, they often use the formula in this way. But they're equivalent, they're exactly the same formula. And I'll talk about both of them again, and where they come from and how you can realize they're the same formula. It's just you changing the notation actually changes how the formula looks, but it's exactly the same thing. So that's called the difference quotient. So if I give you a function and I say find and simplify its difference quotient, what I want you to do is actually write this down and actually plug in the function and compute that value. Okay, so let's do some examples here. Let f of x equals 2x plus 3. G of x equals 2 plus x minus x squared. K of x equals x over x plus 2. Find the first thing I want you to find is f of b minus f of a over b minus a. get into this. How do I find that? What do we do? Panic. No, we don't panic. What do you do? How do you find it? Take it one step at a time. F of b, what is that? Hey, just plug in b for x. 2b plus 3 minus parentheses, and this one is super important to write. F of a. 2a plus 3 over b minus a. That's the first step. Let it go through and piece by piece plug things in, right? And the f of b and the f of a, you're evaluating the function at b, evaluating the function at a, and you plug that in. So what will happen now? Simplify a little bit, I'd expand the brackets. 2b plus 3 minus 2a minus 3. Right? The minus is important because this distributed. The 3's would actually cancel. What now?
b minus 2a over b minus a, you can take out the 2 on top.
2 is a common factor now.
Yeah.
So I can factor out the 2. And then I can... What now? Cancel these, right? Because there's a multiplication here. So the answer is 2. What about this one?
Do you replace the x plus h within the g?
Mm-hmm. And so what would that look like?
2 plus x plus h minus parentheses x plus h squared. Okay. Minus.
Yeah, that's this minus.
The same 2 plus x. Parentheses or
Super important to put those guys in over h. Now what? Simplify. What do we do?
Square x plus we expand.
Expand, so let's just recopy these as 2 plus x plus h minus
Right. X plus h.
x squared plus 2xh plus h squared minus 2 minus x plus x squared all over h.
It should still be in parentheses.
There should still be a parentheses. I was just going to ask that, you just don't. I was going to ask, is that correct? And I wanted someone to say yes and not my chocolate. You still need the parentheses because that negative sign needs to be distributed. Right? Remember, after a negative sign, always keep those parentheses there. So let's x plus h minus. So there are already two major places where a lot of students probably would have made a mistake here. I just want you guys to notice. X squared over h. Now what?
you start counting.
Now certain things would cancel, right? The 2 minus 2
X squared.
x x
X squared.
x squared x squared. So now I have h minus 2xh
Minus h squared.
minus h squared all over h. Oh yeah, we can just cancel the h's, right?
No.
Yes, that's the reaction you should have. No! You cannot cancel the h's because it's across a sum. You know. I'll happen if in a test I hear someone say, no! I know it.
You can pull out an h.
Factor out an h, it's a common term in the top. What would I be left with?
Negative
Now you can.
Now you can cancel because there's a multiplication separating these two terms. And so at the end of the day, we have 1 minus 2x minus h. Questions? And times is pretty much up, so we'll stop there. Try the third example on your own and we'll compare answers when I do it in the next class. We haven't finished with 1.1, so there's no homework due for next class, but again, make sure you go over the quiz, reattend the problems, check your answers, read over your notes, make sure you understand everything that happens in this class. I will have a quiz on everything I've done up to this point on Tuesday.